Alright, so hopefully you messed around with it and you tried squaring a sine of an angle and cosine of that same exact angle, and miraculously you always get 1, no matter which angle you use. Anything from angle, 0.5 degrees, anything to really small, all the way up to 89.9999999. It's got to be an acute angle though. Don't use an obtuse angle, you'll get some weird numbers on there that you won't quite understand until Algebra 2. But that's the second identity I want to talk about. And again, we're going to prove that it really works very easily, just like we did in the last one. Replace sine with the ratio that you know it is. Replace cosine with the ratio, in other words, which side you're comparing. We often get lost thinking this is just magic here when you hit the buttons, but this is just a side ratio, comparing the opposite side to the hypotenuse. And then this is just comparing the adjacent side to the hypotenuse. And again, don't forget, we're squaring those values. So this is actually the opposite side value squared over the hypotenuse value squared. We're squaring that fraction itself. And the same thing with the adjacent and the hypotenuse side over here. We're squaring both of those. And then you don't have to do anything with the right side. All we did is substitute the ratio and substitute the ratio. But it might be easy, hopefully it's easy, to just show that really is always going to equal 1. And I'm just going to let you look at that for a second. Why is this equation obviously going to equal 1? It has to do with something else in this chapter we've talked quite a bit about, and we used it in the previous chapter. If you can't see it yet, it's probably because you're not that good with fractions. So your algebra teacher would say, hey, if you don't like fractions, clear them. Get rid of the fractions. How do you clear the fractions in this case? And your algebra teacher would remind you that you multiply the entire equation by whatever the denominator is. So in this case, you multiply the entire equation by h squared. So if you multiply this by h squared, the h squareds cancel, and you have just o squared left over, the opposite side left over. You multiply this term by h squared, and you have just h squared left over, a squared left over, sorry. You multiply the other side of the equation by h squared, and you get h squared. Now, I know you've seen that equation before. Look at that equation. That's a really nice equation. It looks a lot like something else that you've used many times in this class now, and you're going to keep using for the rest of the year. What theorem does that look just like? And it's obvious that's Pythagorean theorem. It's even more obvious when you think about what these represent. What does O and A represent in a triangle? Oh, those are the two legs of the triangle. This is the opposite leg and the adjacent leg squared and added together. And of course, h is the hypotenuse squared. This is just Pythagorean theorem. This thing, this trig identity, is just a funny-looking version of Pythagorean theorem. It's a trigonometric version of Pythagorean theorem. It's the exact same thing. You've got a leg squared plus a leg squared, technically equal to the hypotenuse squared. It's just written in a weird format with fractions, is the way to think of it. So there's a proof of that identity. You know it works. I got a couple examples for you just to verify that it really works. Just to verify that that identity actually works with some numbers on here. So the first example on there, I'll give you a side length of 7, and I'll give you a side length of 24. Take a minute, figure out that hypotenuse. You guys know how to figure out the hypotenuse is. Something you certainly need to be able to do. Determine the length of the hypotenuse. And of course, you square the 7, you get 49. You square the 24, you get some big number. You add those two big numbers together and you get 625. And the square root of 625, of course, is 25. So you're definitely going to have to be looking for Pythagorean theorem throughout the rest of this chapter and beyond. So now we're just going to verify this really works with some actual numbers. Before we just did it with random variables. Now we're just going to show with some numbers that it actually works. We know that's a Pythagorean triple. So if we're going to show sine of A over cosine of A equals the tangent of A, we need to establish where A is. So A is not going to be the right angle. It's either this acute angle or that acute angle. So it doesn't really matter which one you pick. I'm going to throw it over there. It would work, regardless of where you pick it. As long as it's an acute angle, this is going to work. So write it with some numbers in here. Sine of A is the opposite over the hypotenuse. It's 7 over 25. And then do your cosine of A. That's your adjacent over hypotenuse. That's 24 over 25. You guys should be able to see, kind of anticipate what's going to cancel out here. You have these fractions. You might already know the 25s are going to cancel out if you're not sure about it. we do some keep, change, flip on there. Keep the first one, change division to a multiplication problem, flip this, or take the reciprocal of it. And we're trying to show that this really equals the tangent of A. Tangent of A is opposite over adjacent, which is 7 over 24. That's where that's coming from. And yeah, duh. Cross out the 25s, and you get 7 over 24. Beautiful. It works. So just verifying some numbers. Try the exact same thing, and it's going to be messy because you're going to have fractions on there with the second identity. So the sine of sine of A in this case, squared, plus the cosine of A squared is equal to 1. So we're going to use the same sine of A with sine of A here. Is opposite over hypotenuse again. That's the 7 over 25. And we're squaring each of those quantities. Oh, you can't see all that down there, but there it is. Sorry about that. On the bottom of the previous one. Sorry about that. So we got the fractions canceling out, and we were just showing the tangent really was equal to the tangent after you cancel things out. Cosine of A, of course, is the adjacent side over the hypotenuse, and you square both of those values, and we're just going to hopefully show these fractions out to 1. 49 plus the 576 you got before, they really do in fact add up to 625. And of course we know that 625 over 625 is 1. So just verifying they work on there. Alright. Sort of a transition here. I'll give you an example to try to dive in and try on here. I'm going to give you one of the ratios. You've done a problem like this earlier. You can call that angle A if you'd like, if you want to include a drawing on here. It does make it a little easier if you make a drawing. I'm going to give you cosine of A. I want you to find the other two ratios. I'm going to kind of reveal answers on that in part 3. So good luck. Go for it. You have done this before, so it's not that different. You don't need the trig identities to do it. Just sort of an opportunity to review a concept we did earlier.